Good morning, guys. Today we're going to work with linear systems and setting them up, the word problem portion of them, setting them up. And we're going to use the idea of totals and units to get this done. We're going to let the numbers do the work, let the words put the things that are like together, and be able to set up these linear system word problems. So let's look at this first example. A candy manufacturer wishes to mix two candies as a sales promotion. One candy sells for $2 per pound, while the other candy sells for 75 cents per pound. The manufacturer wishes to have 1,000 pounds of the mixture and sell it for $1,350. How many pounds of each type of candy should be used in the mixture? So if we look at it, first thing we need to do is identify our variables. What is it we're looking for? We can see that they want us to find how many pounds. Be very specific about your units. The variables are not going to be candy 1 and candy 2. Or $2 candy and 75-cent candy. It's pounds of each type of candy. So we'll let T be the pounds of $2 candy, S be the pounds of 75-cent candy, being very specific to identify the units of the variable, the pounds of candy, and what distinguishes between the two, especially since the units are the same on both of them. So pounds of $2 candy and pounds of 75-cent candy. We're going to let those units do the work for us. Now it's time to set up our equations. When I'm working one of these, I always look for totals because totals make the easiest equations because things add up to give us totals. Your variables will add to give your totals. So if you look in here, the first total I recognize is 1,000 total pounds of candy. So if we've got that 1,000 pounds of candy, we know that a totaling equation is always a sum of the variables. Now we could put something with the variables, make some kind of coefficients on those variables, but let's check and see if we need to. It's 1,000 pounds of candy. We'll look at the units on your variables. Pounds and pounds of candy. So T is pounds of one kind of candy, S is pounds of the other kind of candy, and the total is 1,000 pounds. So since the units of the variables match the units of the total, then we don't have to change them. We only put numbers on the variables. We only put coefficients on the variables when we're trying to change the units. These units already match. Pounds of one candy plus pounds of another candy should add to give us the total pounds of candy. So since those variables units already match the total, we don't need any coefficients. That equation is finished. Now let's look at our next total. $1,350 total dollars. Well, again, it's a totaling equation, so it's a sum of the variables, T plus S. But now if we look at it, the variables are measured in pounds, and this total is measured in dollars. Well, those units obviously don't match up. So we need to put something with the variables to turn them from pounds into money. Well, if we look at the other numbers we've got in the problem, $2 per pound and 75 cents per pound. Well, that's where it talks about money, and this per pound is perfect because per implies that we're talking about a rate. Rates can never stand by themselves. A rate always has to be multiplied by something. Okay? A rate always has to be multiplied by something, and the per is what they have to be multiplied by. So this $2 per pound tells me I have to multiply $2 times some pounds. Well, that's good because our variables are measured in pounds. This 75 cents per pound tells me that 75 cents has to be multiplied by some pounds. So the units for the rates are actually going to tell us that these are going to be our coefficients. So if I've got my total money, I've got to put my money rates onto my variables to turn them from pounds into money. So $2 per pound was for our first candy, our T candy. 75 cents per pound for our 75, our S candy. And then that's going to set up that equation. $2 for 1 pound times the total number of pounds gives us the money for all the T candy. 75 cents per 1 pound times all the number of pounds is going to give us the total number of money for S candy. So all the money from the T candy plus all the money from the S candy gives the total amount of money. Put the things that are alike together. Pounds plus pounds equals pounds. Money plus money equals money. And then we clean it up, and this is our actual system that we'll solve. T plus S equals 1,000. 2T plus 0.75S equals 1,350. From there, you can go about solving any way you want to, whether you want to do substitution or linear combination, or later on when we get into matrices, we'll look at some techniques for solving that way. But we're just working on the setup portion today. All right, next example. To conduct a science experiment, students must use 1% and 10% acid solutions. How many milliliters of each solution should be combined to produce 90 milliliters of a solution that is 3% acid? So what this is telling me is I've got two different mixtures. One of them has 1% of it is acid. The other one, 10% of it is acid. So when we combine a certain amount, we're going to get 90 milliliters. And of that 90 milliliters, 3% of that's going to be acid. Well, let's identify the variables so we can answer the question. How many milliliters of each solution? So that should be our variables. The milliliters of the 1% acid solution and the milliliters of 10% acid solution. Notice, very important here, that the units are not milliliters of acid. It's milliliters where this much of milliliters of solution that happens to have this much acid in it. And milliliters of a solution that happens to have that much acid in it. It's not milliliters of acid. It's milliliters of a solution with acid in it. And the 1% and 10% are just telling you how much of each of those is acid. All right, so we've identified the variables, being very specific to units. Okay, take the time, write it out as far as what your units are, because the units will do the work for you. Now let's start building our equations. So we need a total. First total I see is 90 milliliters of solution. It doesn't say 90 milliliters of acid. It's 90 milliliters of solution. Well, it's a totaling equation, so add up your variables and then check your units. The variables are measured in milliliters of solution and milliliters of solution, and the total is milliliters of solution. So if the units of the variable match the units of the total, we don't need to change the variables, so we don't need to put any coefficients on there. Coefficients change your variables. They change the units of each of these terms. So if they already match milliliters of solution and milliliters of solution to be total milliliters of solution, leave them alone. We only put coefficients on if we need to change the units. Let's look at our next total. The next total is going to be this 3% acid. Again, a percentage is a rate. It has to be multiplied by something. It can't stand alone. So I can't just say my total is 3%. It's got to be 3% of something. So it's got to be multiplied by something. So 3% of what is acid? 3% of the 90 milliliters is acid. So if you've got a percentage that's a total, you've got to be multiplying it by something. And that's a pretty good indicator of how your equation's going to be set up. It's a totaling equation, so it's a sum of the variables. Now let's check the units to decide if we need to put coefficients on there. So as I look at this, A is milliliters of solution, B is milliliters of solution. Milliliters of solution does not add up to give us milliliters of acid. So what we've got to do is put some acid information in there. So 1% and 10% acid will tell us what portion of each of these is acid. So we know 1% of this first one, so 1% times the first one will tell us its acid contribution. 10% of the second one, so 10% times the second one, will tell us its acid contribution. So when we do 1% of A, that tells us all the acid we got from A. 10% of B is all the acid we got from B. And all together is 3% of 90 milliliters is the total acid. Let the units do the work for you. Let's clean it all up. What you're going to solve, A plus B equals 90. And 0.01 plus 0.1 equals 2.7. Where'd that 2.7 come from? That's the 3% of 90. That's how we set up this type of problem. Third example. Company A produces a whole wheat flour that has 13.6 grams of protein and 2.5 grams per unit. Company B produces a whole milk that has 3.4 grams of protein and 3.7 grams of fat per unit. How many units each of whole wheat flour and whole milk must be mixed to make a dough that has 75 grams of protein and 15 grams of fat? First thing you do, identify your variables being very specific to units. So it says find what? Find how many units of each. How many units of flour, how many units of milk? That's going to be the variables. And in this one, the units happen to be the word units. If they had been talking about these per cup, per, I don't know, pound, per liter, it doesn't matter. That would have been our units, but these each said per unit and how many units. So that's going to be the variable, is the number of units of flour and units of milk. So we've identified the variables, being specific about the units. Now let's build our equations. Do we see a total anywhere? A first total I see is 75 grams of protein. That's the total protein for the whole dough. That's after we've made the mixture. So we have 75 grams of protein. Well, since it's the total, it's a sum of the variables. So F plus M. Now, F and M are measured in units. So units of flour plus units of milk will not equal total grams of protein. To get grams of protein, I've got to add up grams of protein, put the things that are alike together. So I go back to my problem and look for grams of protein, and I see it in two different places. 13.6 grams of protein per unit, 3.4 grams of protein per unit of milk. So the 13.6 is our protein for our flour, 3.4 is our protein for our milk, so we put them with what they go with. 13.6 grams of protein for flour, 3.4 grams of protein with milk. Protein plus protein equals protein. Next total, 15 grams of fat. Again, it's a total, so it's a sum of the variables. Variables are not measured in grams of fat, so I've got to put some grams of fat rates with each of these variables. So if we look at it, 2.5 grams of fat per unit of flour, 3.7 grams of fat per unit of milk, and we just put the things that are alike together. 2.5 grams of fat with the flour, 3.7 grams of fat with the milk. Fat plus fat equals fat. Protein plus protein equals protein. Let the units do the work for you. If you will clearly identify your variables in the beginning and being specific to units, and you will write the words in there for each of these, it becomes very obvious how to set each of these up. Clean it up to turn it into a system that we can solve. 13.6F plus 3.4M equals 75, and 2.5F plus 3.7M equals 15. What variables you actually use don't matter. You could be using X and Y, A and B. I just typically will grab something that describes what the variable actually is, especially if I'm not graphing. Just makes it easier for me to put the numbers that go with them, the coefficients that go with each of them together. And finally, 3 blouses and 4 skirts are on sale for $72.50. 5 blouses and 2 skirts would cost $66. How much does a blouse cost? How much does a skirt cost? So first thing we do, identify your variables. If you want to pause it for a second and try to do this one on your own, you can, but I'm going to keep moving on. How much does a blouse cost? How much does a skirt cost? So that's what your variables are, the blouse cost and the skirt cost. So a cost is a rate. How much does one of them cost? So I'm letting B be the dollars per blouse, S be the dollars per skirt. Don't write the word cost because cost is not specific enough to units. Write dollars per and dollars per. Now we set up our equation, so we need to first find totals. So what's the first total we see in this problem? $72.50. That was the total for that first sale. So $72.50 for the first sale, the first grouping of blouses and skirts. Adding them up, because it's a totaling problem, so it's a sum of the variables. We know right now that there's no way this could be the equation because B and S are rates in this problem. That's the dollars per blouse and the dollars per skirt. We've already said a rate can never stand alone. It always has to be added to something or multiplied by something. So we're going to have to multiply the dollars per blouse times the number of blouses and the dollars per skirt times the number of skirts. Putting the things that are alike together, 3 blouses times the cost of each plus 4 skirts times the cost of each gives us the total cost. Let's look at sale 2, and we see a total of $66. Adding up B and S, but since they're rates, we know the units don't match up. Dollars per plus dollars per does not equal total dollars. So we've got to get rid of that per by putting in the number of blouses and number of skirts. So that $66 came from 5 blouses and 2 skirts. So 5 blouses times the cost per blouse plus 2 skirts times the cost per skirt gives us our total cost. Clean it up. 3B plus 4S equals 72.5. 5B plus 2S equals 66. That's how you use totals and units to set up systems of equations, to do the evil word problems that math teachers always ask you to do. It's a word problem. It's just math written in word form instead of math symbols. Use the what you know about math, that the like stuff has to go together. Let your units do the work for you and put the like stuff together, and you'll never have problems setting up 2 variable linear systems again. That's it. We'll work on these in class tomorrow, and I will see you then.